Alright, so today we're looking at transformation of trigonometric functions. So our learning intention is to gain the knowledge of translating and dilating trigonometric functions. So we're going to understand, we'll be successful, we can apply that the vertical dilation is the same as change in amplitude. A horizontal dilation is a change in the period. A vertical translation is change in the center. And a horizontal translation is change in the phase. Okay, so the first thing is the vertical dilation. So this is going to be a change in the amplitude. Okay, so if you get y equals sine of x, which I've done this in degrees, and I've done this in radians here. So 1 radian is 180 and 2 radians is 360. So half of it is pi on 2, and this is 3 pi on 2. So I'm going to, we know that sine goes from 1 to -1, and it looks like this little S shape. Okay, so if we have y equals 2 sine, the amplitude, the k value has increased. So what happens is we're going to multiply every y value by 2. So if it's 0, 0 times 2 is 0. 2 times 1 is 2. That stays at 0. Negative 1 times 2 becomes negative 2. So negative 2 and 2, and then that becomes 0. So the amplitude in our function has stretched, by 2. And obviously if we have a scale factor of 1/2, it will shrink. Sorry, it will compress. Okay. So if y equals k sine x or y equals k cos x, then it has an amplitude of k and a vertical dilation of k. If k is 1, it stretches. Greater than 1, it stretches. If it's between 0 and 1, it compresses. If you get y equals negative k sine of x, negative cos sine of x, then it is reflected about the x-axis. So let's do this. So we've got negative 4 sine of x. So the amplitude is 4. Okay. And instead of going like this, we're going to reflect about the y-axis, about the axis. So it's going to look like this. Now all of these are between 0 and pi. So just be aware of that. Okay, this one we've got negative 2 fifths of cos x, so 2 fifths is negative 0.4. Okay, and it's a reflection. So originally it will go, cos function will look like that, but we're going to reflect it. So what's going to happen is it's going to look like that between 0 and pi. Okay. Note that we don't have a vertical dilation for tan, because tan goes to a very large number. Alright. So horizontal dilation, this is a change in period. Okay, so our normal sine curve, will look like that. It has a period, so this repeats again between 0 and 2 pi. So it has a period of 2 pi. Okay. And so what happens is if x has a period of 2 pi, sine of 2x means that the period between 0 and 2 pi happens twice. So it's a scale factor of a half. Yeah. So between this half, I have to have the S shape happening. And so it still goes from -1 to 1, but I'm going to do my first period between 0 and pi. Yep, so here would be pi on 2, and this would be pi on 4. And that would be, so 180 plus 45, no, sorry, 90 plus 45, so 135 over 180, so this is 3 pi on 4. Okay, and then it will repeat here again. Yep. So 2 pi means 2x means the period happens twice between 0 and 2 pi. Okay. All right. Y equals cos of x. Cos of x goes like that. It also has a period of 2 pi. So the period means so it goes like this before it repeats, and that's what we mean by a period. Another repeat. Okay, so from 0 and 2 pi, it does one pattern. So now we're going to do cos x over half, so which means it's going it's going to repeat this period in this time frame. Yeah, it's going to stretch. Okay, so if that happened once, if that was going to be 0, so here's still 1, that was 0, it now moves over to here. This negative value moves over to here. That will move over to here, and that will be at 1. That's still -1. That's 1. Okay. So if you got y equals sine a of x or cos of a of x or tan of a of x, if a is greater than 1, the function is compressed. If it's between 0 and 1, it is stretched. Okay. Let's do tan. So tan is a little bit different. Tan looks like this. And you can see that tan repeats its pattern within one period. So that's half a period, half a period. So its period is pi. All right. So if we want 3x, we're going to compress it into 3 sections. So that's the usual place where the asymptotes would be. And now what we're going to do is we're going to compress this within 3 sections. there's another, so we're going to have to split that into 3. Okay. Now, if we have a of -1, so if the function is negative, it reflects about the y-axis. So we're going to do this one. We're going to have y equals -2 of x. So the normal period goes like that. But now it's going to happen in twice as fast. So it's going to happen like that. And what's going to happen is then it's going to reflect it about the y-axis. So it's going to look like that. And once you've drawn it, you can rub out any unnecessary pencil markings. Okay. So we've got y equals cos of x. So cos, remember, goes like that between -1 and 1. And now, because it's half, it's going to stretch its period by a half. So it's going to go like that. Okay, now it's going to reflect about the y-axis. And when we reflect around the y-axis, we actually get the same. Yep. And the reason we get the same is because cos is an even function. Sorry. And sine is an odd function. Yep. And so is tan. Yep, so just remember that cos is an even function. So when you have a negative, it will still give you the same type of function. All right, so now we have tan. Tan happens like that. It's now happening for every 1 period. We're going to do it into 2. Yep, we're going to split it in half. So there's your 1 period. So and then we're also going to reflect it. Like that. Okay. So a vertical translation. Okay. So you've got y equals sine of x. If you have the center for this is going to be at y equals 0. Yeah, it balances. This is symmetrical about this axis. Yeah, so this is actually y sine of x plus 0, where the center is 0. If you have it as plus for sine of x, cos of x, then if c is greater than 0, it translates the center up. If c is negative 0 is less than 0, it translates it down. So something like this, where we have something like that. If we're translating it plus 3, it means that it will go up to 3. So it would go from 4 to negative, so 4 to 2 as its range. Okay. And if we had cos, so cos look like that. So once again, the center at 0. It now shifts 2 units. So your range, so the center now becomes at negative 2. Your range becomes negative 3 and negative 1. Okay. So a question like this is, what is the center of y equals sine x plus 2? Well, the center is 2. Yeah. Here the center for cos of x is at negative 4. And here we have, when y equals sine of x plus 5, we've got the center of 5. Yep, and you should be able to calculate the range straight away from that. Alright, now we have a horizontal translation, and this is a change in the phase. So if the phase of y equals sine x plus b, or y equals cos x plus b, then, or y equals tan x plus b, then the phase is b. If b is greater than 0, it shifts to the left. If b is less than 0, it shifts to the right. So for example, here we've got y equals sine x. We want to have a phase of pi on 2. Okay, so what's going to happen is this point is going to move pi on 2 to the left. Okay, because it's greater than 0, it's going to go to the left. This point's going to go pi on 2 to the left. We're all basically moving everything to the left pi on 2 units. Okay. Here we've got pi on 4. Okay, we're going to move it to the right every a quarter of a unit, quarter of pi. Okay, so here that's 1. We're moving it a quarter pi, quarter across. Quarter across. And you get that. Okay. And that's everything. All right.